मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
So, this is the second lecture, mechanics of metal forming. As last time we have seen the course content, whole course content for this particular course. Before starting the mechanics part, let us see first the internal or lattice structure of a metal, how it looks like. Especially it concerns to deal with the deformation process in metal forming. So how the crystals are arranged, what is the role of crystal, what is the how this crystal grow. So let us answer some of the questions before starting, like these are some of the questions. Let us answer these questions. The first question is, what is the internal structure of a metal and how does it look like? So we would be going through details to this question and the properties of metal that depend on their crystal structure. All properties, it depends on what kind of crystal structure it has, and the defects, if it is there in the structure. Most of the structure has got certain defects, so depending on the defects, what kind of changes are to be there. Second question is, what is the metal alloy, how it is made. So one can see that alloys are a combination of two or more metals elements which have enhanced the property as a result of their combination. So this we would see. Then the third question could be that how are the properties of a metal is affected by various heat treatment. Under cold condition, how these properties is affected, and under hot condition, how it is affected. So the metal crystal's structure can be already whatever structure it has, it can be altered by processing methodology or some kind of treatments to make them more useful in various applications and for different applications. Like the last question that one can look for in this lecture, how can scientists visualize and study the altered properties of a metal. So because the metal crystal structure can be observed now at a micro level, at micro level, and at nanoscale level. Now it is possible to observe the structure with respect to if there is any change in property, and then it correlates. So the properties of a material are a direct result of its structure. If one like to change the property, that means one has to affect the changes in material structure itself. As a result of the ability to control the structure through processing and ability to develop new structure through various techniques. In fact, to go into the details of structure, let us see there are bonding before structure, how atoms, different atoms of metal at micro level behave. So if we look into the atomic bonding, so what is atomic bonding? It's a chemical bond. Generally a chemical bond is the physical process which is responsible for the attractive interaction between atoms and molecules, and that which confers stability to diatomic and polyatomic chemical bonds. Generally there are two types of bonds, primary bonds and secondary bonds. Primary bonds can be ionic, it can be covalent, it can be metallic. So when we talk of the ionic bonds occur between charged particles. If you look into this figure, the metals usually have 1, 2 or 3 electrons in their outermost shell. If you see the nucleus, and then you can see the there. So here you see at the outer orbit 1 electron, here it is more than 1 electron, and how these two, when there is a 7 and 1, so there is a excess and here is a deficiency, so how they join to make bond. So this is what, so non-metals have basically 5, 6 or 7 electrons in their outer shell. So this you can do, you can see how the things are going to make bond. So some of the common features of ionic bonds are like, it is very hard. First, this kind of bond creates hard. It has a good insulators, and it is basically transparent and brittle or clever rather than to deform. So the ionic bonds are the second, having these properties. Secondly, the metallic bonds, in metallic bond, instead of sharing electrons between two atoms, the electrons in the outer shell are shared amongst all the atoms in a lattice, with all the atoms which is positively charged. So these atoms are attracted to the negatively charged cloud of the electrons, and the movement of the free electrons means that the metallic bonds materials have good thermal and electrical conduction. So you can see here these electrons are free here, and these are the metal ions, So this is it forms a metallic bond, whereas the secondary bonds that these two falls, the primary bond, secondary bonds are weak bonds, and that exist in substances such as water. So to understand the secondary bond, let us see the van der Waals bond. If you look into this figure, where the van der Waals bond is formed from an electrostatic charge in adjacent atoms. It is present between long chain molecules in polymers especially, bonding the chains together. When it is stressed, when these bonds are stressed, these molecules are stressed, the bonds break easily and causing the material to deform. So this is a very popular van der Waals curve, which is the force between, and one can see that when the distance is less, the force is very high as it goes on. So this is non-contact, this is the contact situation. On this side it is a repulsive force, attractive force. So the secondary bonds are weaker bonds. If you see the bonds out of these different types of bonds, the different types of bonds has the different energy associated. Like the covalent bond, the energy gigapascal, if we look into, if it is 1000 covalent bond, for an example, the diamond has got a covalent bond. Ionic bonds, which is of the order of 30 to 100 gigapascal. Ionic bond like your salt and ceramics. Then the metallic bonds, which is again of the order of 30 to 150 gigapascal, like in metals. This is the hydrogen bond. It is very low. It is of the order of 8 gigapascal, and generally it is in ice. Is an example where the hydrogen bond is there. And van der Waals bond is very weak, as it was shown. It is of the order of 2 gigapascal, and generally it is formed in polythene. Let us see the arrangement of atoms. Atoms they arrange themselves to make materials, and because of the external forces, how they deform. Let us look into that. So atom bond, they bond together, different atoms, to form aggregate. That depends on the manner of atomic grouping. Materials are classified as 3 different categories, like molecular structure, crystal structure, and amorphous structure. One can see is how the lithium, niobium, and oxygen atoms are dispersed, and how they are forming in a very ordered manner. One can see here, this is amorphous silicon oxide glass structure. So it's the question how atoms rearrange them under the different forces that was discussed, forming a bond. So let us see a crystal. That the previous one, where the formation of crystal, there are 3 basic crystal structures of metals, and most metals and alloy crystallize in one of these 3 very common structures. So first thing, that one is the BCC structure, second is FCC structure, and third is HCP structure. I am not going in details of this, but one can see that the coordinates, that is the coordination number having low valences like 2 for oxygen, 3 for nitrogen, or 4 for carbon is found as non-metals. In the BCC structure, the nearest neighbor one can see from the figure are at the corner of the cube, which is surrounding the metal atom in the center. One can see here it is at the center, where these atoms are arranged at the faces. In hexa compact HCP and CCP structure, the atoms packed like stacked cannonballs or ballard balls in layers with a 6 coordinate arrangements, and each atom also has 6 more nearest neighbors from layer above and below. One can see like here. For an example, the body centered structure, one can see the sharing. This shows the corner atom is shared by the neighborhood. This is the arrangement. How? So the body centered cell has atoms at each of 8 corner like cube, plus 1 atom at the center. This is the center here. This is the bigger atom, and here the smaller atoms all together. Similarly, the face one can see here the arrangement. So it's a structure. Similarly, the third one can see it's quite packed. So it has a 3 layer in fact. The top layer where there are 6 atoms that arrange themselves in the shape of a hexagon, and 7 atoms that sits in the middle of the hexagon here. The coordination number of the atom in this structure is 12 therefore. You can see the actual arrangement here. Now, so this is what the basic crystal structure for metals. One can see the common metal and their corresponding structure. For example, aluminium is a FCC structure, chromium is a BCC structure, copper has FCC structure, the iron, alpha iron is FCC structure, gamma iron is BCC structure, iron which is delta has got BCC structure, lead is a face FCC structure, nickel FCC, silver FCC, but titanium is HCP, quite compact. Tungsten is BCC, zinc is HCP. So one can see that. Now let us see when these structure combines. So how a crystal is formed. For an example, if we see the iron, so iron has got body centered cubic structure, which is displayed by the iron and many other elements. The unit cell, which is shown in white, outlines a cube with an additional atom in the center. And similarly for the gold, if you see, it is again a cubic close packed structure which is displayed here. This kind of which shows many other metals. The structure is a cube with an additional atom in the middle of each cube, and the gold has around 12 nearest knife burrs. Therefore, alternatively the structure can be thought of as stacking layers of close packed atoms. Let us see a simple crystal structure for gold. On the gold one can see how the structure is formed. On the other hand, here you have one layer neighborhood. On the zinc one can see it is a hexagonal packed, and therefore it has 12 neighbors. In this case, it is two diagonal layer which highlights and rotated to match the zinc model with this. Here you have two layer, one layer is highlighted here, one layer which is repeated stacking of two layer offset one from the other. A possible third offset position for a layer can also be seen and is used in gold model here. So there is one model. So this is two diagonal layer model. So this is how a crystal structure one can think of. How the then grain is formed when you solidify, that is in solidification process, wherein it is an important process in manufacturing, where the complex shape components like billets, slabs are formed of metallic alloy. The control of the grain structure and of the microstructure associated, their phases which develop during solidification process, is a key issue for the optimization of the final mechanical properties and of the subsequent heat treatment. Why I am going through these details? Because the behavior of the metal as a macro level would be quite clear if you could understand the crystal lattice, their formation and all that. When a molten metal is cooled, for an example, it is cooled down, the metal atoms settles out into a crystal lattice. Given enough time and ideal condition, the crystal lattice can grow to a very large with a perfect internal crystalline structure. Ideal conditions are seldom found, in fact, and the reality is that almost every solid metal exists as jumble of crystals of varying size. Each individual crystal in the body is called a grain, therefore. So every crystal it is a grain. That means these grains are crystalline structure that have lot of imperfections, impurities in there, which would distort the crystal lattice. Therefore, if there is pure metal, the unit crystal, that we have seen the three types of the unit. If there is impurity, that will distort it. So how recrystallization happens? As I told you, at the cold condition there is no recrystallization. When you heat up, these crystals reshape. So recrystallization is the transition from the liquid to the solid state and occurs in two stages. Number one, first the nucleus is formed, like this is the small nucleus, So nucleus is formed, and then across the nucleus the crystal is grown. One can see here it is growing. This is the second is growing. to understand the mechanics of solidification, one can see here that the square grid, the red square grid, one of the grid represents a unit cell, and therefore in A there is a nucleus formation, then B and C it is the growth of the crystal. You can see here more crystals are formed, and third, because of the growth, boundaries are created. Once these all are filled, you will find that there is a boundary across this. This is one boundary, this will create across one boundary, this will create another, and therefore this is called as the grain boundary. So these grain boundaries are weaker regions. So when you deform, the material would like to slip across these grain boundaries. The material properties of metal and alloys are concerned with these boundaries and grains. So let us see how much do the properties of a metal and alloy vary with different processing. I must say it has a great deal. Let us consider one example here, and let us have a hypothesis situation. For example, upon graduation, if you go to work as an engineer for Boeing company, your job is to work with aluminum companies to help them produce high strength alloy. Why? Because a large jet airplane, the weight is the total of around 500 ton for a bigger jet plane. Of that total, 50 ton is the cargo part, and 150 ton is the plane structure, and the remaining is the fuel which is used. That means if you can triple the strength of the material is the structure, that's the aluminum. If you can anyhow increase the strength of the aluminum, you can reduce the mass of the structure to around 50 tons and increase the cargo to around 150 tons. Okay, so look at this here. If you look into here, this has been the pure aluminum, that is 99.45%. Its tensile strength corresponds to 4 into 10 to the power 3 psi. If it is pure, but it is cold drawn, so when you dry it, the mechanical properties are improved. So it is increased to 24 times. 24 multiplied by this much. Now, if you take aluminum alloy, which is precipitated and hardened, it goes to 50. So what we look into? By simply chemical and physical manipulation, we have already increased the yield strength 12 times over annealed aluminum. Yet the yield strength of a perfect single crystal of pure aluminum is 4 into 10 is 10 to the power 6 psi. So we still have 3 order of magnitude to go. So how to increase the strength? That's the matter. Another thing, as I told, if there is any defect, so the defect in metallic crystals, which is non-directional bonding, has an important impact on the mechanical properties of metals, as it was shown earlier. Because there is no strong preference for one atomic position over another, the structure is not greatly improved by the vacancy of a single atom or the dislocation. We would see in detail what is vacancy and what is dislocation. of a group of atoms. These mistakes in packing of metallic atoms within crystals are called defects. The deformability of metal is the direct result of defect in the crystal structure. So, defects in materials like aluminum and iron are responsible for the 3 order of magnitude difference between the yield stress of the annealed polycrystalline samples and perfect single crystals. It is the defect that reduces the strength. There are several different kinds of defects that can be found in metallic crystals. One kind is called as vacancy, that is a place where an atom is missing in the structure. A dislocation, that is called as dislocation. On the other hand, dislocation is a line defect. It runs somewhat like a string through the crystal. A dislocation is the result of one atom or group of atoms being pulled slightly out of the position. With respect to perfect crystal packing, a third kind of defect is called grain boundary. As I told, the grain boundaries are very weak. It is a two-dimensional interface between the two different crystal grains in a solid sample, and therefore, since the two crystals have in general different orientations, the structure do not match up exactly in the interface, and therefore a bubble raft computer simulation one can see to see into these. We would be showing it in the next slide, how the metal crystallize in a close packed arrangement, and how defects from form in their structure, and how defects like dislocation and grain boundaries are relatively mobile there. We will be going through. Let us see what is elastic deformation. To these grains, along with as a substrate, if you look into the elastic deformation, when there is a sufficient bond is there and external load is applied to a metal or other structure material, it will cause the material to change the shape. This change is in the shape is called as deformation. So what we are looking into the plastic deformation in metal forming. So what is deformation? So there is a change in shape, and that would be called as deformation. When it is elastic deformation, means it describes the effect of a metal which returns to its original shape when a load is removed from this. For example, if this is the initial shape, if the external load is applied, and when these loads are removed, it comes back. So this is called as elastic deformation. Whereas in plastic deformation, if you look into, when the stress is so great that which forms a permanent plastic deformation, and if you remove the external force, the shape will still be change, shape will be continued. So here, if you see here, the change in the lattice structure with deformation, if you apply here, if you remove this, it is changed. For an example, now it is changed. So the original state, this is original state, This is the elastic deformation with vertical forces. So this is also elastic deformation with diagonal. This is the beginning of the plastic deformation upon a slip line. So it's a slip line, and the deformation that proceeding upon further slip lines, these are generated. So the plastic deformation will result into a permanent deformation, and therefore it is because of the dislocation. You see the dislocation movement, how because of the dislocation is an impurity, as I told you. But let us see what is strain hardening and work hardening. So work hardening is a in metal is a strained bond. When a bond is strained, the yield point, the yielding as the material yields, when the strength of the material exceeds from the it remains, the external force exceeds the strength of the material, that is the yield strength, and if you further increase the stress to produce the additional plastic deformation, and the material and the metal apparently becomes stronger and stronger. As you increase the load, the material experiences more strength and more difficult to deform. Therefore, one can see this figure here. This is what is the stress strain. If you apply here, so this strain hardening happens because of the slipping, the movement of dislocation across the slip line. We would see later. The grain shape is very important, and if the grains are uniformly distributed, we call it as isotropic. If it is not uniformly distributed, the crystals, then it is anisotropy, and therefore the anisotropy in a single crystal, the physical and mechanical properties, it differs from its original one, metal. When the properties of a material vary with different crystallographic orientation, the material is said to be anisotropic. Let us take an example to understand the situation of strain hardening. For example, if you take many times a copper wire and hammer it many times, so you will find that it becomes stiffer, and it is possible to hang a hammer from it in that case, because it stiffens, and therefore the dislocations move to a crystal gain boundary during work hardening, and work hardening takes place. Effectively halting their motion, that is the motion of your dislocations, at the same time making the individual crystal grains smaller. When the wire is annealed in a flame that is heated at a slightly higher temperature, so these crystals rearrange them. The crystal grains grow and the dislocations reappears. The copper becomes more ductile and bonds are easily cold work, and therefore one can see the role of strain hardening, and therefore for making brittle and hard edges, even you can see the blacksmith hammer and the knives and all that, sword, how they make them harder, and sometimes the same thing is working metal. So in the cold condition one can use it for one can take the advantage of strain hardening. As far as the cold working is concerned, if you look into the structure and then the associated recrystallization and the hot working, so one can see here at the higher temperature the new crystals are formed and the nucleation and growth as it was shown, and these new crystal grains grow and further the grains are formed and therefore the strain hardening comes, because this dislocation moves and it passes across a grain boundary and then it becomes difficult and therefore you require more load, and that's the reason how the cold working or the strain hardening takes place. With the recrystallization, the mechanical properties return to their original weaker situation and more ductile states are formed. So one can see here that this figure how the internal residual stresses, the hardness decreases, strength, and this is the ductility increases. One can see the recovery and the grain growth. One can see here this is the different, this is the internal residual stresses. So the recrystallization, particularly in hot working, it happens within a given range of temperature. For different alloys, the recrystallization temperature is different. So we would be looking into the in next lecture the part of the details. Thank you very much.